Dear students, today let me discuss on the topic of deriving the field components of a parallel planes. In this video presentation, I'll be briefing about the construction of a parallel plane, then the necessary basic equations which is required in order to solve the field components, and we'll be doing some simplification methods, and finally we'll be achieving the field components. Okay, now let us see about the construction of a parallel plane. A parallel plane is something like considering two conducting planes which is separated by a dielectric medium. The dielectric medium might be in the form of an air, and an EM wave is propagated in between the separation of two conducting planes. Now let us see in the diagram wise. So these are the two parallel planes. Consider conducting planes which is having a similar length and dimensions, something like length, breadth and height, and which is also having the same conductivity. And in order to analyze the field components, we need some coordinate systems. So for that we consider a rectangular coordinate system here. Okay, now let us see the complete physical structure. Consider two planes which is separated by a distance, say x is equal to 0 to a. So in between these two planes, an electromagnetic wave is going to be propagated, and the wave is going to be propagated in the direction of z axis. That means the wave will start somewhere here and it will be flowing to the outer part here. Okay, based on this, there occurs some reflections in the planes. Finally, you will be achieving some field components. So that is what we are going to achieve in this derivation. Okay, further continuing with the derivation, what are the necessary equations which is required? So in order to solve this problem, we require Maxwell's equation as well as wave equation. Now let me start with Maxwell's equations. As we had studied in electromagnetic fields, what is Maxwell's equations? You have first equation, that is Faraday's law, where del cross E is equal to minus of dou B by dou T. And the second equation is from Ampere's law, that is del cross H is equal to dou D by dou D. Okay, now based on these two equations, we are going to start our derivation. Now we need to convert the above two equations in phasor form. If I convert the above two equations, then the equation will be in this form, that is del cross E is equal to minus of j mu w h, that is omega is the angular frequency and mu will be the corresponding refractive index, and del cross h is equal to j omega epsilon into E, since we know that B is equal to mu h and D is equal to epsilon E. So we need to convert dou by dou T in terms of j omega in both the cases. Then you'll be getting the phasor form of the above Maxwell's equation. Okay, now from equation 3, we will be starting our analysis. So in equation 3, you have LHS as well as RHS part. Now we are going to start with LHS of an equation in rectangular coordinate system. Similarly, we will be finding what is the equivalent coordinate system, that is in RHS part. Then we will be simplifying it. Okay, from equation 3, first the LHS part will be del cross E. As you know that del cross E is a curl, so you can represent it likewise. So since we are representing del as well as the electric field intensity E in rectangular coordinate system, so this will be del cross H. Now if I simplify this matrix, as you know that we will be getting something in terms of AX. So AX, so you need to cross multiple and you will be getting its corresponding term. Similarly for AY component as well as for AZ component. One modification I made here is for AY component, I have a negative sign. I can also replace it as a positive sign by interchanging its sign. So that is one step I'll be doing here. Okay, after that for RHS part, you have minus j omega mu h. So here we need to represent h in terms of rectangular coordinate systems as hx, ax, hy as well as hz, the representation in terms of rectangular coordinate system. Then if you multiply it, you will be getting a result something like this. Now compare both LHS component as well as RHS component. So here you have something as AX term along with some value. Similarly here also you have something as AX term along with some value. If I compare these two equations, I can get some result something like this. After comparison for AX component, I'll be getting a component sampling like this. Similarly for AY component also, if I compare it, and similarly for AZ component also, if I compare it, then I'll be extracting three set of equations. Now repeat the same steps for the second Maxwell's equation, that is del cross H is equal to j omega epsilon e. So you try to solve it and you try to achieve the same result. Okay, after solving it, you will be getting another three set of equations in this form, say as equation 6. So this equation is extracted from second Maxwell's equation. Okay, what is the third equation we are going to use here in our analysis is wave equations. As you might be studied about wave equation, this is the wave equation for electric component as well as for magnetic component. So again we can do the same process by representing the same two wave components in terms of rectangular coordinate system. So the corresponding E and H terms will be represented with respect to x, y as well as z also. Okay, now you will be getting another equation in the form of wave equation which is represented in rectangular coordinate systems. Okay, before finding the field components, we need to make some assumptions. Now let us see what are the assumptions to be made. So the wave particle will be moving in z axis. So the field varies only in x and y axis alone. At that time, if I consider the components, let hy be a wave particle, then hy naught is some magnitude part and my exponential term is the propagation, where my wave is going to propagate, that is in the direction of z axis. Now if I partially differentiate this, then I'll be getting as dou hy by dou z. Then if I partially differentiate it, then I'll be getting something as minus of gamma into hy naught into e to the power of minus gamma z. Just compare these two equations. So I can replace it, this particular term, simply as hy. Similarly, I need to find the same thing for the other component, that is for hx, where hx is equal to hx naught into e to the power of minus of gamma z. Similarly, I will be getting another result. Repeat the same things for the other two components as ey as well as for ex also. Then again you will be getting another two components something like this. And one more assumption we need to make is the wave is propagating in z direction, so no variation occurs in y direction, that is the variation in terms of dou by dou y term will be simply assumed as 0. Okay, now substituting all the assumptions what we derived. So something we derived here as all the above four components, now substituting in the above equations.